Let us first talk about converting the AC from the grid, the 230 volts AC from the grid into a DC. How is this done? The simplest circuit would involve a diode. We have a diode, and let us say there is a resistive load as shown like this. So this is R0, and the voltage measured across R0 is called V0. So the voltage measured across the input is V in. This is the 230 volts mains input, and the current that flows through the diode and R0 as I0. So let us look at how the wave shape look like. So I have the y-axis and the x-axis, which is time axis, and let us try to draw this wave shape V in. So V in is sinusoidal in shape, so it is something like this. Let me mark this as V in. And now let us draw what is V0. So V0 will be similar to V in except for some difference. So there is a diode. So diode will pass only the positive part of the input wave shape. The negative part is clipped. This is a clipper circuit. So as long as the anode is more positive than the cathode, diode will be forward biased and pass the currents to flow. The moment the V in becomes negative, which means that the cathode is more positive than the anode, diode will block the voltage, there is no current flow, and the voltage across the output will be 0 as I is 0. So let us draw that part of the waveform. So let me mark these time zones. So during the time when the input is positive, it will get through to the output, and during the time when the input is negative, it will not get through to the output. I will also draw one more axis to mark how the current looks like. So let me mark this as V0, and this is I0, and I0 will appear exactly similar in shape as the V0 waveform, because that is what is appearing across this, and this load being resistive, V0 by R0 will be the current. So current wave shape also will be exactly similar to the V0 wave shape, except that the amplitude will be different, and the amplitude is defined by V0 by I0. V0 by R0 will be I0. So these are the wave shape that you are seeing for this particular circuit. See that the output V0 is unidirectional. So one thing that we have done with this exercise is to convert the AC to unidirectional varying wave shape. It is still not DC in the strict sense, it is unidirectional. So how to convert this unidirectional varying voltage wave shape into a DC wave shape? In order to smoothen the output waveform, this varying unidirectional output waveform, we need to put a filter here across the output. So one of the simplest filters that we can put is a capacitor. The capacitor, by virtue of its physics of operation, will not allow voltage across it to vary instantaneously or discontinuously. So voltage will be smoothened across the capacitance, because voltage is 1 by C integral of the current through it dt. Because of the integral action, there is a smoothing effect on the voltage across the capacitance. So let us now consider operating point here, and let's say this point is moving along the input wave shape here, moving along the input wave shape that is applied. And as this point moves along the input wave shape, what is the output voltage and how is the evolution? Let us see that. So when you are here at this point with respect to the input, the output is also 0. And let's say that the input wave shape point moves, and in the first cycle the capacitor is not yet charged. So as this is moving, as this voltage potential is moving up, this is always going to be lesser than this. Diode is forward biased and the capacitor voltage will follow the input. So it will follow in this fashion. And then let us say when this point moves further up, this will also move along with the output voltage, will move along with the input. So like that, this will move till it comes to the peak of the input voltage. Till this point comes to the peak when the output voltage, the voltage of the capacitor would have followed the input and come to this point. Now here is when the action begins. When the point moves further down, you will see that the input voltage is, if you take this instant of time, the input voltage is lesser than the output voltage. The input voltage is lesser than the output voltage corresponding. So which means that the anode is having a value which is lower than the cathode, and the diode is reverse biased and cut off. So which means that the input is now cut off from this portion of the circuit, and only the capacitor is delivering power to the load, whatever the stored energy in the capacitors. So it is going to go in its natural RC time constant way. So it's going to decay exponentially. So as the input is traversing along this path, it is always, the anode is lower than the output, and therefore the diode is out of picture. So the output voltage is decaying through the load in an exponential fashion till it reaches this point of intersection. So when the input voltage has again risen in the next positive half cycle to some point here, the capacitor voltage would have decayed to that point. When after that the input voltage rises above the output voltage, diode is forward biased and the capacitor will try to follow the input. So it follows the input in this fashion, and so on. It repeats cycle after cycle. So let us now also look at what happens to the current. See, the current is going to flow only during the period of time when the diode is forward biased. So when is the diode forward biased? During the first cycle, this entire portion of the time from 0 to the peak, the diode will be forward biased, and during subsequent cycles, from the point of intersection to the peak, you will see the diode is forward biased. So which means only during that time there is a chance for any current I0 to flow, as we have indicated here, to flow, which will flow to the combination of the capacitance and R0. So you will see the current flow only during this portion. So here in the first cycle, as the capacitor is totally discharged, starting from 0 charge, there is no energy in the capacitance. The entire energy has to be put into the capacitance, and therefore you will see a larger current. And subsequent cycles, there is a minimum charge, there is a charge available in the capacitor, and only the charge which it lost during this period, during the period when the diode was off, only that charge has to be made up, and therefore the currents will be slightly lower. So this is how the wave shape of the output voltage and the current I0. Here the I0 current is not this. We had marked I0 when the filter capacitor was not placed. So I0 here implies a combination of C and R0. So this current I0 will split into a capacitor current and the current through R0. So now it is time to change the notation here of the current. We will shift the symbol I0 to the actual load resistance and indicate separately the capacitance current, and this current will become the diode current. So let us make this change in notation. So I will erase this and mark it as D. This is the diode current ID, and this will be the diode current axis ID. So this red curves is basically the diode current, which will split into two parts: the AC part, which will go through the capacitance, and the DC part, which will go to the output. The capacitance cannot handle DC part. The capacitance will always have an average zero current, and therefore the AC part will flow through the C. So we will mark this as IC, or the capacitance current, and mark this as I0 now in green. So an averaging effect of the unidirectional current flowing through the diode is what will be I0. So I0 is something like that. So this I0 is not purely DC. It will have a varying component, because the output voltage is also not purely DC. It is basically V0 by R0, which will appear as an average value here. The ripple of the output will get compressed by R0. Consider only the output wave shape as shown here, the half wave rectified output wave shape, and let us draw the output with the filter under steady state conditions, under the equilibrium conditions, where you will see that this output gets filtered due to the presence of the capacitance. There is some ripple, and then we should be able to control the ripple amplitude by design. So let us see how we can go about finding the value of this capacitor. Now let me mark off these 2 points. The peak of the input sign here occurs. So this is one marker, and there is another marker at the next peak here. Okay. Peak to peak is one period, isn't it? One period, and in our country, this one period is because it's a 50 Hertz waveform. One period is 20 milliseconds. If you are talking of angle from this point to this point, the angle would be 2 pi. So let us say that we have this another critical point, this point of intersection. There is these 2 portions that I'm going to divide this time, and if I call this as alpha, so for the alpha duration you will see that the capacitor voltage is following the input, and all other duration in that period, in this period, and all other duration, the capacitor is cut off from the input because the diode is reverse biased and capacitor is only supplying energy to the load. So that would be 2 pi minus alpha. So during 2 pi minus alpha, capacitor is supplying to the load, and during the period alpha, during the time period corresponding to the angle alpha, capacitance capacitor is getting replenished. All the energy that it lost during this period will get replenished here, plus the load is also being supplied by the input because the diode is conducting during that time. So let us say that this portion is the portion where capacitance is only purely supplying to the load or not, and this capacitance or not combination is disconnected from the input. And this is the period when the capacitor is getting replenished and the load is being supplied by the input directly. So I'll call this point here as V1, the peak value as V1, and once the capacitor is discharged, this point of intersection when the diode again turns on, we will call this as V2. So basically the ripple amplitude is V1 minus V2. Let me now draw coordinate axis here. So let's say if you are talking of power on this axis over time. So in this one period, what is happening? So in this one period, let us say that the load is drawing a constant power of P0. So let the load draw a constant power P0. Now there are these two segments. This is one segment and this is another segment. And let us mark that. So I'll mark that, and then here also I mark. So during this segment, capacitor alone is supplying power to the load. So let me hash that. So this hashed portion, you will see that is the energy that is given by the capacitor. This is half V1 square. The capacitor started off with energy half V1 square, then ended up with it having an energy half V2 square. Half V1 square minus half V2 square is the amount of energy that is put into the load. So let us write that down. Half C V1 square minus half C V2 square is the amount of energy that is given to the load, and that would correspond to this. Now if you want to find the power, this is energy. If you want to find the power, it is the rate at which the energy is given. So this repeats every cycle, and that is at T period time, that is at 50 Hertz rate. Now this is equal to, now this is P0, and then there is a duty cycle in that period, P0 into, this is this value, 2 pi minus alpha divided by 2 pi. So this would be the duty cycle, so which means that is the amount of power this should represent. So from here C is equal to P0, 2 pi minus alpha divided by 2 pi. Now this T also we can take it to the other side, divided by, now you have half C V1 square minus half C V2 square. So if I take out half C, you will see that V1 square minus V2 square can be written as V1 minus V2 and V into V1 plus V2. So V1 plus V2 divided by 2, this 2, I'll take this 2 here, into V1 minus V2. So what is V1 plus V2 by 2? It is nothing but averaging of this and this. So you have V1 and you have V2. V1 plus V2 by 2 is somewhere in between, and this is V0. So V0, which is V1 plus V2 by 2. So I will call this as V0. V1 minus V2 is delta VR, that is the ripple voltage. This is again an input specification. So if I rewrite 2 pi minus alpha by 2 pi into P naught, so divided by this V naught delta VR, and T I will take it to the denominator and call it as F, which is the frequency of the input wave, which is 50 Hertz in this case. So further simplifying, I'll say C equals 2 pi minus alpha by 2 pi into P naught is V naught into I naught. So I will say that it is I naught divided by delta VR into F. So this would be the capacitance value equation, where alpha, what is alpha? Alpha is this angle. So if this is the peak value, this value would be cos of the peak. So V2 should be cos of this V1 cos alpha would be V2, right? So if this is V1, we will write that down, where then alpha would be cos inverse of V2 by V1. So by this way you can calculate the value of C. Alpha is known, just now we found that it is cos inverse of V2 by V1. I naught is the load, it is an input specification given for design. Delta VR is the ripple specification given for designing the circuit, and F is the frequency of the input wave, and that is 50 Hertz in the case of India. Let us also look at the current waveform so that we can select the appropriate diode. Now let me include this milestone marker and extend this below so that we can draw the current wave shape. And let us see that during this time the diode is conducting. During this time the diode is conducting. Rest of the time the diode is not conducting. So the diode will have a wave shape something like this, the diode current, and the average value of that will be I naught. Now I naught, I am showing it as a DC with negligible ripple. This is I naught. The AC part alone will flow through the capacitance. Capacitance will not have a DC part or an average value flowing through it, because there will be charge buildup, and in the equilibrium state, as there is no charge buildup, the current through the capacitance, the average value of the current through the capacitance will be 0, and a pure AC current will flow through the capacitance. So through the capacitance, whatever this red colored waveform minus this blue colored waveform, that is minus I naught, will be the current that flows through the capacitance. The red marked waveform is the one that is flowing through the diodes. Because this is a very odd shaped waveform, it is difficult to actually find the peak value of this current. So what we can do is alternatively find an equivalent flat top peak of the current. So we can redraw or revisualize the current wave shape like this, so that approximately, let us say you have a pulsed kind of a wave shape flowing through the diode, have pulse wave shape, and that is the IM that we can call the peak value of the current or the max value of the current. We know this is alpha and this is 2 pi, and therefore we can say that I naught is equal to Im into duty cycle. So I naught is Im into the duty cycle is alpha by 2 pi, and therefore the peak value in terms of the known value I naught, which is given, it is a specification load specification, and Im is equal to I naught into 2 pi by alpha, and alpha we found out that it is cos inverse of V2 by V1. Now IC, as I said, is this diode current minus the average value, minus I naught. So this is the capacitor current. To find the peak inverse of the peak inverse voltage for the diode rating, so we see here that this diode, when it is off, now let us say that when the load is very, very low, then the capacitor is charged to the peak value V1. Then the worst case for the diode when it is off is when the input is at its negative peak. So at that negative peak, so you have a value of V1 here and a value of V1 here. The V1 at the input is negative, so it will be V1 minus V1, which is 2V1. 2 times this peak value is a possibility that can occur across the diode. So you should rate it greater than 2 times V1. So choose the PIV, the peak inverse voltage for the diode, to be greater than 2V1, 2 times the peak of the input. The peak value can be around I naught 2 pi by alpha, and the average value is I naught. So this way you can choose the appropriate diode and the value of the capacitance and the capacitance. One point that you must note is that when you choose the ratings of a device, like a ratings of the diode, and let us say the peak inverse voltage what you are getting is 2 times V1. So let's say 230 root 2 is 325. 2 times that is 650. Do not choose diode which is exactly 650 volts. You have to give a buffer margin. There are several unknowns, several uncertainties and variabilities, and there can be apart from noise, there can also be surges. So you should give a safety buffer while selecting the devices. So whatever may be the rating of the device that you have chosen, do not apply a stress more than 75% of the rating. So if you are having a 100 volt device, do not apply more than 75 volts as the voltage stress for the device. It could be diode, it could be BJT, it could be IGBT, MOSFET, as a general thumb rule for any device selection. So let us say you have a current, you want to choose, you have a current of 7.5 amps, then you choose a device of at least 10 amps. So if I am having a device having a current rating of 10 amps, then as a thumb rule, do not allow more than 75% of its rating, which is 7.5 amps, to flow through it. This is to give a buffer safety margin for all the devices that you select, to take care of some degree of uncertainties and unmodeled dynamics which we are not aware of.